Hi, my name's Brad Neal with the University of Indianapolis. And in this video, we're going to talk about section 9.3 in the OpenStax Chem 2E textbook. Video is going to be a little different from the other ones because I'm going to try to point out in the actual reading itself some of the key things that I want you to take a look at. And then we also will highlight a couple of notes here on the screen for you as well. So let's go ahead and get started. So the first thing that's here in the reading is this gas density and molar mass. What they're trying to get you to start thinking about is you can take this equation PV equals nRT, and you can really manipulate it a whole bunch of different ways. So, for example, you can figure out what the molar mass of a gas is using its density by remembering your density is this mole or mass over volume relationship here. If you have mass over volume as this relationship here, you can substitute, rearrange V so that this is then, I'm just going to show you. So you could do this whole D equals MV thing, and you could convert that over to volume equals mass over density. And so then if you go into PV equals nRT, you can substitute this stuff in. So you got P M over D being your density equals nRT. And then if molar mass, like what they're saying here, and it's like fancy M, if molar mass is mass per mole, if you do just a little bit of rearrangement of this equation right now, you can get to this final expression that they've got. The density of a gas is equal to its molar mass times its pressure divided by RT. So you got a couple of different things that you can do here when you're thinking about this. One, if you feel good with math and remembering your relationships, you can always just solve this out for yourself. Totally legit, no reason not to do this, except for maybe you don't like math. If you don't like math, you probably want to go ahead and memorize this equation or be really comfortable with this density equation here. This is just density of a gas. The metacognitive thing that they're trying to get you to realize is you can make valid mathematical substitutions here as part of this process with these different equations. So you can manipulate these equations till the cows come home, and it's going to be totally fine. They walk through this example where they give you they ask you what's the density of molecular nitrogen, and they show you here's how you would plug the stuff in. STP, just as a reminder, I think we've covered this in case we didn't. Standard temperature and pressure. So it's 1 atmosphere and a temperature of 273 Kelvin. So that is something you just need to have memorized. Down here, they just kind of rearranged that equation yet again, the PV equals nRT, to show you how you can continue to manipulate this. It turns out that the gas law chapter here is really a combination of the concepts used in chapters 1 through 4. So for example, when we're talking like here 9.12, determining the molecular formula of a gas from its molar mass and empirical formula, you have to remember what molar mass is and how it's different from empirical formula for this problem to make much sense to you. So it gives you this information about what the composition is, yada, yada, and you can do all the stuff we did back in chapter 4 to figure out your empirical formula. If you're looking at this and it's not making a ton of sense to you, I strongly recommend that you go back and review that chapter 4 material, because this chapter the gases here are predicated on you understanding and being able to do stoichiometry, understand the mole ratios, etc., what moles mean. You're going to find a lot of times in these gas questions, especially as we go on, they're going to be like the gas stuff concepts are going to just be a layer on top of some other concept. So up here, there was this empirical formula data that was given to you as part of the problem. From that, you're able to figure out your empirical formula. Because it's a gas, they incorporated the ability to find your molar mass of a gas using your modified ideal gas law equation to figure out what your molecular formula is. And then you piece the pieces together from chapter 4, where you say your molar mass divided by your empirical formula mass, that gives you your ratio. And so then that gives you the ability to figure out what your molecular formula actually is down here. This is a nice little example where they just pretty much show you it's pretty darn easy to actually do this in the lab. So this might look like it's pretty theoretical, but in the lab space, it's not that difficult to do, to figure out molar mass of a gas or a volatile liquid, as this example has written out. So this first part is really, you have a choice. You can, if you're feeling comfortable with math, you can manipulate PV equals nRT using expressions that we've talked about previously as part of the course. And then boom, solve these equations for yourself, or just memorize the 3 equations that we've needed thus far in order to solve these kinds of problems. It really is up to you. There's not like one right way or wrong way to do that. Dalton's law of partial pressure. This image is kind of nice. I want to just talk through it here a bit. Basically, what Dalton's law of partial pressure and the ideal gas law is saying, gases, like we're making some assumptions. And one of the assumptions is that the identity of a gas does not affect the pressure. The size of a gas particle does not affect the pressure. It's the number of collisions against the wall of the container that affects pressure. So if you've got a combined container over here, the pressure that you're reading is the pressure that's generated by your blue particles, your purple particles, and your yellow particles individually. If they're all in just one container, all you have to really do is just count up the total number of particles. And the total number of particles leads you to your total pressure. But if there was an easy way to isolate out just the yellow particles into a container, you could take all the yellow particles out and then put that in a container, and you could figure out what the pressure that is being created just by the yellow particles is, or the purple particles, or the blue particles. So Dalton's law of partial pressures is telling us each individual gas will have a pressure, and if we add all those individual gases pressures together that are in a mixture, we can figure out what the total pressure is, and that total pressure represents the pressure being produced by the mix of stuff. So that's really what we're getting out of Dalton's law of partial pressure. Now, one of the ways that it's written out is up here at the top. This P total equals PA plus PB plus PC, on and on and on for as many components as you have. Excuse me. Again, at this point in time, we've been talking about how the pressure of something is dictated by the number of collisions. More collisions, more pressure. One of the ways to increase your number of collisions is to increase the number of stuff. See some of the previous videos that we've done. So if we wanted to figure out how many particles that we actually had, there's a number of ways that we can do that. We can think about the stoichiometry that we've done in chapter 4, where you use balanced chemical equations to figure out how many moles of product that were generated. And that's totally valid. You can still use all those kinds of techniques here in this chapter. For this chapter, they're introducing yet a new technique called the mole fraction. And the mole fraction is just like most of our other ratios. It's part compared to whole. Mole fraction just gets defined as the A, like number of moles of A, like component A in your total mixture, and N total is the total number of moles in your mixture. So if we're looking at this example up here in the diagram, illustration, whatever, we could say the number of particles, the yellow particles, we could count those up, and we would divide that by the count of the total particles in this container. And that's our mole fraction. You do not want to multiply this one by 100. Some of the other kinds of ratios that we've done, we've multiplied by 100. Mole fraction, you don't. Mole fraction is going to be a number that's going to be less than 1. Or it's going to be 1. The only way it's 1 is if it's a pure substance, though. You don't have any, it's not a binary mixture. Or it's not a mixture, period. So example 9.14 here gives you the count of how many moles of different kinds of things exist in one vessel. So every single one of these things here has a different amount of moles, but they all have the exact same temperature and they all have the exact same volume. Because they have they have to have the exact same volume because they're all in the exact same container. And if you think back to your thermochemistry, we talked a little bit about thermal equilibrium. Like all of your particles in the exact same container, given enough time, they're going to reach thermal equilibrium, meaning they're all going to have the same temperature. The average, same temperature. So if that's the case, we can use PV equals nRT to figure out the partial pressure, the pressure for each one of these individual components, because we're given them a number of moles of hydrogen. And your book went through and they redefined PV equals nRT in this form of the equation. They just isolated the pressure variable, which is fine. And they were able to plug in the number of moles of hydrogen times R, which is constant, times your temperature, which the problem gave you, or divided by your volume. And they were able to do that for every individual component. So the pressures that result then are all the partial pressures for each of the individual gases. To figure out your total pressure, you would just add all three of these partial pressures together. And there's just a large variation in kinds of Dalton's laws of partial pressure problems. But at the end of the day, they all come back to this relationship right here. Your total pressure is equal to all of your individual components' pressures. Now, how you figure out your individual components' pressures, there's a variety of ways of doing that. Like this relationship that we have right here, the pressure of component A is equal to the mole fraction of component A. Remember when we talked about mole fraction? Multiplied by the total pressure. This expression, this pressure of component A, works because we're talking specifically about the mole fraction of component A. And that mole fraction of component A is going to then, and that the mole fraction of component A is going to isolate A. And since we said pressure is very dependent upon the number of particles, this works. There's some math that we could go through to show you a mathematical derivation, but it totally works. Here in 9.15, it's, like I said, there's a lot of different ways to ask partial pressure problems. Nice alliteration there. And this is just a different way of doing that. The only way to really, there's no way that I can explain to you all the different kinds of partial pressure problems, because there's just variations and tweaks that make the number of kinds of problems like this just huge. What I can do, though, is tell you, write down all the things that you know that are given to you in the problem and what they actually are defined as. Then start writing down equations and see how things are related to one another. So, for example, this problem in 9.15, it's telling you how many moles of oxygen and how many moles of nitrogen or nitrous oxide. And it tells you your total pressure. Well, if you've got a mixture and it's only oxygen and nitrous oxide, you could figure out your mole fraction of either the oxygen or the nitrous oxide. Because the definition of mole fraction is take your component and divide that by your total. So if you're trying to figure out the mole fractions of oxygen and nitrous oxide, boom, you just use your definition. Your partial pressures, we just talked about the previous expression up there where you would take, to solve your partial pressure of oxygen, you take your mole fraction of oxygen, multiply that by your total pressure, and boom, you got that. Now the units that you use here, it's not unit dependent. It's not like PV equals nRT. You do want to keep track of your units though. So whatever your pressure units are in, for your total or for your partial, etc., you need to make sure that they are all, anything that you're working with, all have the same units. But you don't have to be in atmospheres. There's nothing here there's no constant like R in PV equals nRT that dictates, you need to be using blah as your pressure unit. Now, one of the ways that you can collect a gas sample is this little apparatus here. You had a homework problem that was associated with collecting a sample of gas over water. Well, this is what it means by collecting it over water. The punchline of this is, you have some kind of chemical reaction that's occurred here. It releases gas. The gas goes through this tube and it goes down, 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 and up into this container. Now, this container was originally filled with nothing but water all the way up to the top. It's just the gas that's getting generated is coming out here and it's pressing out some of the volume of water that was in this container back into this vessel down here. So you can measure the change in your water volume in this container, and that's going to give you a good indication of what the volume of your gas is. Or you can have a graduated cylinder that you do this in, or an RMI flask like the image is here, with graduated marks on it, and you could figure out what volume of gas you have collected. Because there's water here, the water is going to evaporate to some degree. And you know that because anytime you've ever put water on a countertop, you dry it off, but there might be a little bit of water left. You're like, cool, it doesn't really matter because the water is going to evaporate. Well, a little bit of your water here evaporates into this collection flask, into the gas phase. So not only do you have up here your collected gas from your reaction, but you also have a little bit of water vapor. So any pressure that's associated with the gas here isn't just for your reaction gas, it's the pressure of whatever your product gas was. It's also partial pressure of water. And this is where Dalton's law again would come into play. The partial pressures of water are super well studied. Here's this table here that's here in the reading, right? Here's all these different temperatures that you might be at, and here's the resulting, and here's the corresponding partial pressure of water at that temperature. This is a thing that you can almost always find in a book. These are values that are incredibly well studied. So when you have problems like 9.16 here, when it says argon is collected over water at this temperature, and the total pressure of your system, it didn't say total pressure, but it's the total pressure. The pressure of your system is shown in blah, blah, blah. What is the partial pressure of argon? Well, total pressure is pressure of your argon plus partial pressure of your water. Where do you find your partial pressure of your water? A table like this. So you'll have to look this up, or it's going to have to be given to you. There's also these like huge old tables. Well, this isn't as huge. Yeah, there we go. Yeah. Now we're talking. Now we've got all these different partial pressures here. So here's your water density. Here's your vapor pressure of water at different temperatures, yada, yada. You can always find those. So this is a number you look up. This is the number you're looking for. This is the number that is given. Easy breezy lemon squeezy. Last thing, I hope, is our gas stoichiometry. Basically, everything that you did for stoichiometry before still applies in gas phase. Remember how I was saying, like, a lot of the times these problems gas problems are just an additional layer on top of some other kind of problem that you've done? A gas chemical stoichiometry problem is just that. It's stoichiometry like we've already discussed in class back in chapters 3 and 4. You just now are adding in PV equals nRT as part of the mix. Here's like a way to think about it. In terms of balloons, which is fine, what you'll usually find are problems that might look like this, where you are here in 917, where it's telling you, or it's asking like what volume of oxygen is required to react with a volume of propane, measure the same temperature and pressure. There's a couple of different ways that you can solve this problem. This problem goes through and it is actually having you react volumes of gas with volumes of gas. Another way that you could do this, because volumes of gas reacting with volumes of gas is totally fine, Avogadro's law. The other way you could solve this problem, because if this volume of gas thing makes you a little uncomfortable, is you could do you could take your volume of gas and your pressure. So it's saying what volume of gas given a pressure and a temperature, and you could solve for using your ideal gas law. You could solve this problem. It requires more steps to use your ideal gas law to solve this problem, because you're going to have to figure out things like your number of moles, which isn't going to be as straightforward for this kind of a problem. You could do it still, because you would say in this, the 27 liters of propane, you would be able to figure out from your 27 liters of propane the number of moles of propane that you actually have. If you know your number of moles of propane that you have, then you can figure out your moles of propane that you had. Did I already say that? From your moles of propane, you can use your balanced equation and say for every 1 mole of propane, it reacts with 5 moles of oxygen. And then you could take your normal stoichiometry stuff. So all this really is to say here in 19.7 is you've got a couple of different ways to do this. If you don't feel comfortable with the way that this problem is laid out here, you could just use your pressure that's given, the 760 torr, which is going to be 1 atm. 1 atm. You have a volume of 2.7 liters of propane. You could figure out what your number of moles of propane are. You use your R value. And you could use your temperature. 303, yeah. And here is going to be your moles of propane that you've solved for. You can use your stoichiometry, the 1:5 ratio of moles of propane, etc., to continue on to answer this question. So stoichiometry is stoichiometry is stoichiometry. The thing about this one now is we're adding in gas laws. Since you're thinking about gases, you always have to remember PV equals nRT is in there somewhere and will be used somewhere. 9 and 18, pretty similar situation here. The difference in 918 is you're doing dimensional analysis with respect to cubic feet. Cubic feet is just a volume. It's a volume measurement. And so they're working through the process of saying, well, if you know what your volume measurement conversion factor is, based off of your stoichiometry up here, it's a 3:2 ratio. If you have 3 billion cubic feet of hydrogen, you can generate 2 billion cubic feet of ammonia to come up with your final answer. Another problem in this regard, though, they do walk you through more explicitly the process like I just showed you here on the handwritten notes. And then you have more reading, just kind of FYI information. So you look for ways to incorporate chapters 1 through 4 here in the gases, because that's what they're asking you to do. They're saying take the stuff that you already know in terms of dimensional analysis, take the stuff that you know in terms of your stoichiometry, put it together, and add PV equals nRT on top of it. And that's really what 9.3 is all about. If you have any questions, comments, or concerns, please let me know, and thank you very much for watching.